So let's begin. So first of all, let's recall what we have been doing last class. We were talking about the derivative, and the derivative means what? It means slope of the tangent line. And geometrically, the derivative means what? Could anybody remind me? What's the geometric idea of a derivative? So if you look at a curve, what happens? What do you do to a curve to see the derivative? You understood my question, guys? It should be, the answer should be floating immediately in text or anything else. Straight line. You see, guys, you should see a video. You think derivative and you think curve. What do you do to the curve to see the derivative? What word do you, what's the magical one or two words that you use? Two words. Zoom in. Thank you, right? We're on Zoom. Zoom in. And if you zoom in, you see a straight line. Yes? And why is it so obvious that that will be the derivative? For the very simple fact that when you zoom in, you are looking at a microscopic section, which means you're looking, so to speak, over that microscopic section. The points are almost the same, right? Almost the same point. So when you zoom in, you see the line. What do you do when you take the derivative? You select 2 points on the curve. If those 2 points are very close, that looks like a tangent line. The closer they are, the better. So the more you zoom in, the closer the points that you can place together, that would look like a line. Is that clear, guys? Very intuitive. Yes? Now, if a function is differentiable, the C word, then the function is what?
Continuous.
Continuous. And that means what, guys? That means that continuity just means the curve is whole. You understand? Because look, why is differentiability implies continuity? Zoom in on the curve, you see a straight line. A straight line is a particular version of whole curve. There are many other versions perhaps, but well, yes, smooth straight line. Straight line, you might say it's smooth, it's obvious, okay? The word smooth means that you don't cut yourself. Good? And that's the idea of differentiability. So differentiable functions are smooth. Example of what, Francis? So that's a concept, you see. So you have to think, what do I mean when I say derivative, right? So I think a curve looks like a straight line, right? It's just you have to first have concept, and then you can see examples of that concept, I would say, right? So anyhow, let's ask this question again. I mean, I think I already asked it and I think we answered it, but let's just review it, guys. Differentiability implies continuity. I hope you can do that formally as well, right? Continuity formally means continuity at a means limit as x goes to a of f of x is f of a. Good? Right? So this is a sentence that right away translates to you to the idea of continuity, I hope. Now tell me please and remind me, if a function is continuous, does it mean it's differentiable? So if you have continuity at a point, do we have differentiability at that point? The answer is clearly no. Clearly no. Now why is the answer clearly no? We mentioned that before. This, by the way, guys, I mean, I spoke about it, right? I'm not mixing up classes. I did show you this limit, I think, right? And we calculated it, and this is just formally explaining what continuity is, and we're seeing that the formal definition of it agrees with what we had intuitively in mind. Now, we can zoom in at the peak of a sharp edge, and no matter how much we zoom in, it looks exactly the same. I think I've shown you the computer animation of it if you wanted to see it, right? But you should play it in your mind. You should have that animation in your head. You zoom in at the peak and it remains sharp, correct? Now my question is, guys, you see that in this graph, right? So I mean, I easily can construct examples of those functions. This, for example, is a much worse type of non-differentiability. It's a continuous function, but it has a sort of wedge. You see why I think of it as worse? Because you see that when you think of differentiable, you think smooth. That means you're not cutting yourself. So the more you cut yourself, the less differentiable the curve is. So you see that here, no matter how much I zoom in, the angle between the two line segments that make the curve, the angle remains the same. Whereas if I have this type of wedge, the closer I come to the tip, the shorter is the angle. Well, why does it matter if the function is continuous when it's differentiable, you're saying? Well, again, this is, you see, guys, so when you ask me questions about matter or not, it's like asking why does the word a or the matters, right? It's just a connective structure to understand the big picture. Okay, so what you're learning here, even the biggest concept you have learned so far, they're like bricks. And if you know enough bricks, you see a sort of building, right? And if you want to, if you are impatient and you wonder what building to see, I mentioned that, for instance, right? Much of philosophy, many wars in some sense, I don't think it's true completely, but many wars were religious wars, correct? Religion was a very important aspect of human civilization. And mathematics has, in fact, very significant import on religion, right? Because if you look at what mathematics has to say, right, it will either contradict or confirm some religious ideas. So if you're a religious person, for instance, then you wonder about the soul, and knowing something about the derivatives has a lot to do with the conversation about what is the soul. Understand? Of course, if you're a zealot, it doesn't matter. If you're a zealot, you just pray and you don't think. But if your goal is to understand, if you're supposed to be a sage, then you need to understand. If you don't care about that, you have practical aspects, right? So anything involving ballistics, launching satellites in space, keeping them in orbit, transforming, sending codes, sending in ciphered messages, analyzing waves, listening to music, all of it naturally is described in the language of calculus. So if you want to see the big picture, on my website, I do have the physics book. Sorry for the segue, guys. Just if people ask me, what is it for, or what's the example, I'm trying to give you a perspective of what you're looking at, right? You're staring at a brick like this. It's a brick, okay? Zoom out. If you understand that brick, you see many bricks, you will see a structure. That's what I hope for this class. Good? Anyhow, so you all see, guys, that this wedge merges to a very, very sharp point because the angle goes to 0, correct? Nobody is surprised by that picture. Do you see why this is less differentiable in some sense than this thing? Now, without even doing the calculation, do you see what would be the slope if I approach A from the left? Do you see that if I approach A from the left, how do I tell what's the slope? I just imagine taking 2 points very near each other on that curve from the left of A. Do you agree? Take 2 points very near each other, and what do you see? You see that the line is extremely steep. Do you see what happens? So the slope approaches infinity. Do you understand? When you look at a curve and you analyze what's the derivative, you're analyzing the slope of that line. It's a very easy idea. It would be an asymptote, Francis, for the derivative. If you graph the derivative, then A is an asymptote for it. That's correct. Good. So on the other hand, on the left, if you take 2 points, you understand we always measure in the positive sense of the x-axis. You see this to be the slope, and it will be minus infinity. You understand, guys? The idea is even to ask what they mean and what's the relevance should be, if you understand it, it should be not important, because it's like the knowledge of one word. It's like knowledge of what is effervescence or something, right? They just hear as a word. If it's easy for you to know what it means, then you don't even question what it's for. It's just too easy to bother questioning what it's for. Understand? What's the derivative? It's the slope of the line that you see when you zoom in on a curve. That's one explanation. What else it is? Mathematically, it is the expression of instantaneous velocity. Good. So those two ideas you know immediately. So it's so easy for you, hopefully, that you don't even need to be wondering what it's applied for or not. It's just an obvious fact, right? It's like I tell you there are African and Indian elephants. Okay, right? It's useful or not, who knows? It's just an information. Good. Easy, correct, guys? So do you all see that this is plus infinity, this is minus infinity, and here is an actual example of the function built up of two line segments. So it's 1 minus absolute value of x. It looks like that. Good. And and you understand it, the function is 1 minus absolute value of x. Now the function will fail to be differentiable at x equals 0. Correct? Would you please tell me if I select any point without doing any calculations, please? If I select any point here, again, remember the function is 1 minus absolute value of x. That's my fx. If I select any point here, here is a point A. Tell me, please, what will be the derivative? If I calculate the derivative at that point, what will it be? No calculations, 0 calculations. Right away, tell me. Beautiful. I see. Okay. Francis, almost. Okay. Robert, many of you say 1. Those that say 1 are absolutely correct. Now, why is it so easy, guys? Well, what is that thing on the left from A? It is a line segment. If you zoom in on a line segment, you will see a line segment, right? Which means that the derivative of the line is the slope of that line. When you say derivative in Calc 1 sense, you are just mentioning slope. Yes? With me? You are just mentioning slope. So I see that the equation of this line, look at it, 1 minus absolute value of x. X is negative. So what is that? If x is less than 0, this simply is 1 minus x. Do you remember? If x is less than 0, x is negative, and minus x is positive. Yes? So what I am seeing there is the line 1 plus x. This entire thing is the line 1 plus x. What slope does 1 plus x have? Well, you see the slope right next to the x. The slope is 1. Right? You don't need to do any calculation. 1 plus x, the slope is the coefficient next to the x. Are you with me? Okay, guys? Wonderful, right? If you are with me now, it will not trouble you to tell me what is the derivative at any point on the right of 0. Exactly. That is their minus 1. Minus 1. Very nice. Very nicely done. Minus 1. Now, guys, do you understand why it's minus 1? I don't even need to explain. It's because when x is positive, absolute value can be dropped away. And we have 1 minus x. And you see that the coefficient of x is minus 1. And of course, look at it. What happens if I try to calculate the derivative at 0? If I try to calculate the derivative of 0, I can take one point at 0, f of 0, which is 0, 1. If x is 0, this point is 1. I can take that point, and I can take the second point for computing the slope to the right of 0. You agree? I can take the next point. I have one point fixed at the vertex and the other point on the side. I can put the other point to the right or to the left of the vertex. Good. So here, if x is going to 0 plus, it means I pick the point very, very, very close to here. I pick the point kind of here. Here are my 2 points, right? Here is that point 0, f of 0, at which I try to calculate slope. And here is my other point which is x f of x. Yes, and I calculate the slope of that line. I don't even need to do the calculation, but if you want to, we can do it the limit, right? As I did before. I know the slope of that line will be -1. You just told me, at least some of you told me that it's -1. Yes? So if I measure the slope from the right, I see -1. If I measure it from the left, I will see +1. Do you see that? So I see always slope +1, always slope -1. So no matter how much I zoom in, because zooming in means that I'm just seeing more, I'm just focused on the vertex and I'm seeing less points, but I still see points left and right of the vertex. Good? So that means that this limit does not exist. However, the derivative, we have a right derivative and we have a left derivative. Right derivative means if you approximate from the right, you see a straight line. In the left derivative, if you approximate from the left, you see a straight line. Clear? Wonderful. And that's that calculation, guys. And again, there is something about this picture. I hope you understood what it means, guys. This picture, notice that there was one point where the function wasn't differentiable. Good. I can, of course, create infinitely many points of non-differentiability by simply creating this zigzag pattern, or as they say in German, zackig. I really like the word zack, zack, right? Good. Like this. So you create this situation. Look at it. Yes, you can see every vertex and every every vertex of that, basically, of that polygon. It's called a polygonal shape, I think, or something like that, right? So you can see here is a place of non-differentiability. Here is a place of non-differentiability, and onwards, right? So there are infinitely many points of non-differentiability that I can easily obtain. I can even write a formula for it, but it's not important, right? I mean, if you have a picture, then there is some sort of formula behind it. Why not? Good? Or at least there is a function. I mean, you don't have to explicitly find the formula. Sometimes it's very difficult. We have very few functions that we understand. We only have the algebraic functions that we kind of understand. Understand? So there we have limitations there. But here is the next problem, guys. Now we have this zigzag shape. You can see clearly that you can find a lot of points of non-differentiability, but if you look slightly to the left or to the right of a point where the function isn't differentiable, you see a differentiable point. Do you agree? So look what I mean. You see, if you're here, it's not differentiable, but look anywhere to the right, immediately to the right. By that I mean just move a tiny bit to the right, and you're at a point where you have differentiability. Or if you move a tiny amount to the left, you are again at a point of differentiability. Clear? I'm not sure if I asked you or not, but could you tell me, are there functions that are differentiable at no point and yet continuous? Obviously, if the function isn't continuous, then, right? Could there be a function that's differentiable nowhere and be continuous? You understand what it means? No matter where you look, no matter where you look on the graph, you can zoom in as much as you want. You will never ever see a straight line segment, and that means non-differentiable. Okay, Karen says yes. Did I mention that before? I probably have, right? I did speak about this in our class on Thursday. The tooth, precisely, right? So you all remember, guys. You see, that's how stories kind of combine. If you know, I will explain only roughly why, right? I mean, it's not significant for our class. For many years, mathematicians thought that, even very great ones thought that such examples are not possible, but in the 19th century with Weierstrass and his methods, such functions were constructed, and as soon as one was constructed, many others were. Okay, all you have to create is a function that is very toothy, so a simulation of the megalodon tooth, like this. Okay, if you look at a megalodon tooth, no matter how much you zoom in, you see more teeth upon teeth. You understand? Even the sharks have so many teeth that their scales are teeth. Have you seen it? If you look at the skin of a shark, those are called dermal denticles, and you actually see a copy of the tooth that they have in the mouth. So they're covered in those structures. Okay, they're basically a creature that's one whole giant tooth. So that's what you have. We have such functions. Okay, so what I mean, I had a pretty, here is the actual function. I gave a very kind of poor drawing. I was too lazy. What you will see is that you can just look at you can construct that previous example, and on top of it superimpose it with more teeth, and upon those teeth superimpose it with even more teeth. And when you do that, again, guys, there are a lot of technical problems. You have to prove that it's not a meaningless process, that you actually generate that function, you know, all sorts of things you can try to prove. And I think I did show you a picture of how it looks like. You can just type nowhere differentiable function on Google search, and you will find a sort of picture. Truthfully, you cannot obviously know if a function is differentiable or not by looking at a picture, because a picture is always a sort of approximation to the curve. You can never draw any curve precisely, right? So any curve you're seeing, if you're seeing the curve y equals x squared, you're seeing only the approximation of that curve, but not the actual curve. It's impossible to do, right? So obviously, when you just look at the picture, it's not supposed to be something that convinces you. It's supposed to be something that gives you a sort of intuition and nothing more, right? Everything that you're seeing, obviously you're seeing my photograph, obviously you're seeing an approximation to my face. You're seeing only finite detail. If you zoom in, you will see squares, you will see pixels. Good? Similar idea. Now here is a quick comprehension check, guys. If you want to calculate the derivative of f of x equal to 5x plus 2 at x equal to -7, what answer do you put without doing any calculation? Yes, obviously 5. Very good. You all see why 5, guys, because you look at it. What is this function? This function is a line. If I were to draw it, I would draw a line. So if I zoom in on a line, I see that line. And so what do I report when I ask what's the derivative? I report the slope 5. Right? Derivative in Calc 1 sense is just the report of the slope of the line that you're seeing. Clear? Nothing more. It's such a simple idea. Do you agree, guys? If you understood slope, the derivative is exactly the same thing. It's a slope. Except now we generalize slopes to curves rather than to just lines. Because I think, okay, curve is not a line, but if I zoom in, it looks like a line. And I just measure the line, the slope of that line that it looks like. Good? Idea is very simple. Here, guys, zoom in, looks like a line. I hope I repeated it enough times. I don't need to say it more, all right? So zoom in, if you had to explain what's the derivative, you say, draw a curve, zoom in on the curve. If you see a straight line, report its slope. That slope that you report is the derivative. Clear? Everything, all the limits, everything, all of that is expressing the same. Why is it limit as x goes to a? Because if you zoom in at a, x is going to be very close to a, because this is the width of your screen. The x width of the screen is this, right? So x has to be, if you're centered at point A, the x cannot be far from A. So x is going to A. Clear? Now, guys, don't worry if you don't fully understand what I say right now. It might be a bit useful when we talk about implicit differentiation much later in the course. Okay? I want to tell you that when you move away from calculus, from elementary calculus, you redefine the derivative to mean not the tangent slope, but actually the tangent curve. You understand? And why do you do that? Because there is a geometric perspective that is very useful. From a geometric perspective, look at it. Is this line horizontal? Well, that is a meaningless question. It's horizontal from my perspective, right? If my eyes are parallel to that line segment, it looks horizontal. But if I turn my view this way, now from my perspective, it's not horizontal. Do you understand? There is no up or down. So here is what I mean by that example. There is an actual line. It's just imagine it's just a thin rod, suspended somewhere in space. Okay, so here is that line. You see, this is this black thing here. It's a line. If my point of view is, as I stare at the screen, this is my horizontal, this is my vertical, my x and my y. This line happens to look like y equals to 1 times x plus 0. Do you agree? But if I rotate my perspective and I tilt my head, so in other words, I tilt my head and now my perspective, my eyes are parallel to the line. So I'm kind of lying on the side and my eyesight is parallel to this line. Now the green XY system, with respect to the green XY system that I drew here, the same line looks like 0 times x plus 1. The slope changed, but the line stayed the same. You agree? Slope is a matter of perspective. The line is not. The line is there in space. It appears more objective than the slope. Are you with me? Now, why am I telling you that? Because you can use such ideas to figure out connections between derivatives and derive formulas very easily, right? Derivative in our case is how you report the slope. Let me try to illustrate the connection between the derivative of root of x and x squared. Right, we still are at early stages. If you understand such connections, guys, you will see fewer functions. It will be easier for you to do that. Of course, I'm going to show an example. Okay, an example of the idea, naturally. Okay, guys. So, what is the connection between derivative of y equals x squared and y equals root of x? Between, I will write it like this: derivative of root x and derivative of x squared. Here I didn't bother giving them names. Okay, you understand what I'm doing? I'm saying, okay, we have a root function. Is the root function that very different from the square function? That's what I'm asking, right? Square is when you multiply something by itself. Root is when you try to find a number that when multiplied by itself gives you the result x. Good? So let's try to view this, guys. So let's suppose that I want to understand what is the root of, by the way, so if I have the derivative of x squared, guys, do you remember how to take the derivative of x squared? Derivative of x squared is 2x. You remember how to do that, right? So you can do that simply by calculating limit as z goes to x of z squared minus x squared divided by z minus x, which is 2x. When you finish the calculation, we did it many times, correct? We can do the same process for the root, possibly. Of course, there is also this problem, limit of the square root is in the square root of the limit, right? You have all sorts of kind of things that might trouble you if you actually prove the limit laws. Okay, so let me show you what's the relationship between the derivative of root and the derivative of x squared. So suppose that my goal is to find the derivative of the root. So this is my root function. This is, let's call this my x-axis. Let's call this my y-axis. Good? So this is y equals to, so this is the curve y equals to root x. What is y equals to root x? It has coordinates x, root x. That's the coordinates it has. Good? Now, if I want to calculate the slope at this point, guys, so this point is some point A. So I want to calculate the slope at this point. So I send an astronaut to walk along this curve, and he is looking up, and what does he see? He sees the tangent line. And the tangent line has displacement dy, which is vertical, dx, which is horizontal, right? So if he looks at the point A, what sort of slope will this guy be seeing? That's the question, okay? I can solve that question by placing another astronaut. Look at it, if this point is A, what is the corresponding point here? the corresponding point here is root a. Do you agree? That's what it means. First coordinate, second must be the square root of the first coordinate. Yes? Now, would you tell me, so basically for this guy that walks on the x-axis, his horizontal axis is the x-axis and his vertical axis is the y-axis. You agree? So when he measures slope, he measures rise over run, vertical displacement over horizontal displacement, and that's what he's going to report. Now, I'm going to actually send another astronaut, put him walking on the y-axis. Okay, so this astronaut, could you tell me what formula is, when the astronaut is looking at that curve, what formula does he see? So he is walking on the y-axis. His horizontal is the y-axis. Do you agree? You understand there is no gravity, so it's completely arbitrary what's horizontal. You're agreeing with the green astronaut only because you are sitting on the x-axis. Are you with me? But if you were on the blue with the blue astronaut, could you tell me what formula does he see? So this one is reporting I'm seeing. So this astronaut, the green astronaut, is reporting I am seeing the formula y equals root x. Now, what is the blue astronaut saying, guys? What formula is he seeing? Exactly, but he's saying, to keep the notation, he's seeing the formula x equal to y squared. Are you with me? Guys, what is he seeing? He's seeing x equal, the blue astronaut is saying x equal to y squared. They are looking at the same curve. Yes? They are looking at the same curve. But the blue astronaut, well, exactly, that's my question. Do you see that? I want you to think about it, guys, and tell me, why is it y squared? It's a sort of passive, right? So what's the relationship between x and y? So look at it. If you are walking on the y-axis, what do you observe? You observe that the x-axis is the square of the y-axis. Forget about opposite or anything complicated. You just have to understand the difference between passive and active, right? If I gave you flowers, right? If I am giving you flowers, you can say flowers have been given to me. I mean, at least I like to say such in such passive sentences. Do you understand? We're describing the same event from different perspectives. I am giving you flowers, right? Or I'm saying the flowers are moving away from me. And what are you saying? The flowers are moving towards me. Isn't it obvious? Right? So what is the green astronaut reporting? He is saying, oh, look at it. The vertical coordinate, here is what he's saying. He's saying the vertical coordinate is the square root of the horizontal coordinate. Are you with me, guys? It's such a simple thing. The vertical coordinate is the square root of the horizontal coordinate. Now, what is the guy walking on the y-axis saying? For him, the vertical coordinate is reversed, right? So he is saying what? He is saying the vertical coordinate is the square of the horizontal coordinate. We just keep the labels. If you are not confused by that, then you understand what I'm saying, right? And of course, if you're confused, that's very understandable. What is theory of relativity? It's entirely problematic because of confusion of perspective. You understand? I mean, you have to be able to put yourself in the mind of somebody else and see from the other person's perspective. You understand, guys? I mean, I don't see x or y's. I see this. Okay, what is this saying? This one is when I say y equals to root of x, he's just saying my vertical is y, my horizontal is x. The vertical position is always the square root of the horizontal position. Do you understand the difference between how you think about it and how I suppose that you should think about it, right? I don't see x or y's. I see my horizontal position. The vertical position corresponds to the square root of horizontal position, right? Now, the guy walking on the y-axis, Yes, you can think I solve for x, right? Exactly, right? So I solved for x. That's one way to say that, right? So look at it, right? If I have y equal root x, I can say y squared equal to x. But why did I solve this way for x? It's just very simply that good, Francis, right? That's good that you noticed that. It's just simply that my vertical position is the square of my horizontal position. Do you understand? Now, looking at that slope, right? Look at it, guys. The astronaut walking on the y-axis, if he looks at that point, what slope will he report? Remember, he is walking on the his horizontal is y. What slope does he report if he stares at that curve? That's the formula, right? What slope does he report? Exactly, Robert, to y. But what is y? Y in this case is root of a. Do you agree? So you report, so this guy reports that the slope is 2 root a. You understand? So what is, and his slope is what? His slope is the vertical, which is dx, over the horizontal, which is dy. Do you understand what I'm saying, guys? I imagine it's tremendously confusing, but that's only because you're focused on the symbols. I actually have a great question for you on what when we're regarding colors and confusion of symbols. Very great question. We solved it yesterday. Let's see if you can beat that. Understand what I'm saying, guys? So your entire confusion is just you know this game. I think it's called Beatstroke, not Beatstroke. I forget what it's called. When you let's say have green colored red or something like you say yellow and it's colored red and you're confused. It takes your time to read it. Okay, so that's happening similarly because you're confused vertical, horizontal. What's vertical? What's horizontal? But it's very simple. Look at it, guys. Just focus for a moment. This blue guy, his horizontal is the y-axis. And his vertical is the x-axis. Slope is vertical over horizontal, which is dx over dy. His dx over dy, because we know it's squared function, we know how to take the derivative, we found the limit. It's 2 times that, right? 2 times the horizontal coordinate. Do you understand? When you take the derivative of quadratic, it's 2 times the horizontal coordinate. So for the guy walking on the y-axis, it's 2 times the horizontal coordinate, which is root of a. You with me? If you are with me, tell me if you and then he communicates this to the green guy. And now the green guy knows what slope to report without doing any calculation. So he would say the slope is what based on that information. He says, this guy, his sense of vertical and horizontal is reversed from my sense of vertical and horizontal. Yes. So what slope does he report? Right, guys. So by your silence, we're playing what when where for sure. That one question we will play today. You agree, right? Nobody lives until we figure that what one where question. Because I understand your confusion. No, Eva, not quite. Look at it. Okay, guys. So let me reveal the answer to you. We will do it more. Don't worry. I mean, we'll return to that. My point is this, guys, of course. If you have my perspective, the calculus that is what 1,000 pages long is one page. Understand? You can have one page, and that's enough for you to know all of calculus in the book that you have there, and you can solve every exercise. So what he says is, okay, my perspective, he says, is dy dx, which is 1 over his perspective, which is 1 over 2 root a. So he says 1 over 2 root a, which is indeed the derivative at that point. Are you clear? And what's the benefit of that perspective? You might think, well, it's very difficult. It's not. It's very easy once you understand that horizontal is entirely perspective. It's what your perspective. Are you like this or are you like this? If you're like this, this is your horizontal. If you're like this is your horizontal. You might not believe me because you feel gravity. So your mind is telling you that horizontal is where the gravity is pushing you. If you eliminate gravity, you will not have that sense. Clear? Fighter pilots have problems with it. They have to train against their instinct because when they take off at an incline, they actually imagine they're taking off like this or something like that. So there are all sorts of interesting effects by that. So that's my point, guys, right? We are seeing that straight line. I can calculate the slope. Basically, root of x and x squared are essentially the same curve, just looked at from a different perspective. You see, if you see it from the perspective of geometry, there is no difference between the curve root of x and the curve x squared. And therefore, knowing that x squared is differentiable automatically makes you know that root is differentiable. Okay, the function and its inverse geometrically are, well, they're geometrically they generate the same curve, so they have a lot of similar properties. They are two sides of the same coin. Good, wonderful, guys. Right after that, of course, you all think I'm going to take differential geometry. I hope, right? Be lost in contorted spaces, right? Have nightmares like my nightmares are, because they're scary, right? Good, very good. Here is that picture illustrated. I tried to show it to you here, but we will talk about it again. Okay, guys? Here is the next example. We have the graph y equals f of x with those markings on the graph. You see that? Your task is to draw me the graph of the derivative function. Do you remember what you draw when you take the derivative in Calc 1? You draw the slope. Good? Can you do that? You look at the graph. What is the drawing of the derivative function? That's the question. I'll give you a minute to think about it. Maybe let's do it 2 minutes, okay? Do it in 2 minutes and then I'll describe how to do it. In office hours, after we finish playing at least one round of what, when, where, related to this particular thing, we can practice drawing derivative and all sorts of things like that. right, time's up, right? Okay, let's do it together, guys. Good, thank you, Tzvi. You could kind of report the situation. Look at it, 3 to 3. You understand, guys? What am I recording? For each x, I'm recording the slope corresponding to x. What's the slope on the first section? The slope is constant. The slope is equal to 1 everywhere. Yes? So I will draw myself the line y equals 1. Do you understand why this is y equals 1? I am drawing for each x the corresponding slope to it, which is 1, 1, 1, 1, 1. And notice the phenomenon. You should predict that when you see a constant slope, that means that the small line segments that are building up the curve are all lined up together to form a big line. So the micro lines build a macro line. Clear? So here it is 1. Now what happens here, guys? Look at it. Between 3 and 6, what's the slope here? All you do is you imagine placing a small marker or place 2 points and compute the slope. Or if it's a straight line, you can just use the edges 3, 3 and 6, 3 to calculate the slope. So that's 0. You all see that, guys? A line is calculated from 2 points. So I either place a marker or something straight to kind of give me an indication, or if I can, I select any 2 points that look like they are lying on the same line segment. So because this appears to be a horizontal line segment, I will select the point 3, 3 and 6, 3. Those 2 points are enough to calculate the slope. Good? So that means the slope is 0 because there is no vertical change. So it's 3 minus 3 divided by 6 minus 3. And I draw this line segment. Good? Now, what about this part, guys? The slope here, look at it. I clearly descend, what, 3 units here? I move 3 units to the right, and in those 3 units to the right, I descend 3 units down. So that's a slope of everywhere on this line segment. The slope is -1. Yes? Slope is -1, exactly. Exactly, Jahin. Right? All you do, guys, look at it. It can be confusing. Don't think about where the curve is on the x-axis, the actual curve you're observing. Just think about whether the slope is negative or positive, okay? So this is what you do. Look at the curve, forget about the x-y axis of that curve, and just do this. Good? Now, where the derivative curve is not continuous, look at it over here. That's where we fail to have differentiability naturally. We just have a very sudden jump, like in those Charlie Chaplin movies, that you move up, and then without rolling smoothly to be horizontal, you move up and suddenly you move horizontally. So it's like a choppy movie. You understand what I mean? It's like frames are missing. If you're skiing on that landscape, you're skiing up, and suddenly in no time you're skiing horizontally, and in no time you're skiing downwards. Derivative does not exist at those corners. In general, guys, here is a picture of trying to find the derivative in general. Okay, so again, you see what I try to represent. This black curve I think of as built of many very small line segments. Right? I didn't draw the graph perfectly, but I can draw roughly what I imagine the derivative to be. And I did it in green. Do you see what happens here, guys? So here, maybe you think it's below the x-axis. It doesn't matter. Do you see that this line segment is oriented upwards all the way until I reach somewhere over here? Somewhere over here, it's where it's 0. So that means my slope is decreasing. Do you see why this curve is falling? It's positive slope, but the lines are getting less and less steep. So the slope is decreasing until it becomes horizontal somewhere here. Thereafter, it becomes negative until somewhere here, it's horizontal again. So it's negative, less negative. So first more negative, then stops becoming more negative, and then goes back to be 0. And then here, the slope is again positive until you reach that point, which is where it's 0 again. And then it's thereafter it's negative. Are you clear, guys, how I roughly generated the green picture? All I did is just looked at each line segment and over that line segment, I recorded the slopes. Truly, if I, you see, look at it. If I were to do it truly, if for each line segment, the slope is horizontal. I just imagine more line segments than in my drawing. So the picture that I would have obtained would look like lots of small horizontal lines like this. Right? You understand what I mean? So because over here, over that segment, if it's completely straight, it's over that segment, the actual picture, well, that's not the actual picture, just the approximate picture would look kind of like this until I reach that point. So over here, it would be this segment. Then next, over here, it would be something like this segment. So it would be made of many thin segments. I hope you understand what I mean. What kind of question can be formulated from this? Well, the kind of question I asked, I suppose. Let's say, given the graph of the function, plot the derivative curve. I can show how to do that later. Again, right? So I gave you two examples of how to do that, and the question is later. The point of it, of course, there are many points. One obvious point is I want you to very fluidly be able to understand what's the derivative and see it. You understand? I mean, it's all an attempt for you to become familiar with that very basic idea that the derivative is slope. Right? And if you understood it, then you have no problems here. You have no questions at all. I mean, it's just this is a line segment. Over the line segment, the slope is everywhere the same, right? But truly, the curve is always many line segments, so it's changing. You see, so in my drawing, my claim is in the drawing, I lied to you a little bit, right? So if I were to approximate it with just finitely many small line segments, my graph would look like a bunch of very short horizontal lines that will trace, that will line along that green curve. Do you understand what I'm saying, guys? Do you understand why I'm saying the green curve? If I just consider the small red line segments, the green curve will actually be lots of horizontal line segments, steps. Would anybody tell me what I mean by that? Or you do not understand? Yes. Look at this graph, guys. Look at this graph. Do you see this graph is made of several red line segments or several horizontal line segments? Forget red or not, right? Here is the original curve. Here we see several red line segments. Yes? Do you understand? My first question is, what made the line segments of the derivative horizontal? All of them were horizontal. Can you tell me why all of them are horizontal? Simple question. Look at this graph. All the derivative parts are horizontal. Why is that? No, that's not because there is no, here's a rise. Obviously, there is a rise. All right. Why over this segment from 0 to 3? This is horizontal. Between 3 and 6, this is horizontal. Between 6 and 9, this is horizontal. Why is it always horizontal? Because they're straight lines. And anywhere for any x between 0 and 3 where you calculate the slope, you calculate the same slope. Calculating the same slope, meaning you're tracing a constant. You understand? For what are you drawing here? You're drawing the derivative. You're saying for this x, that's the slope. For this x, that's the slope. So for all the x's you have between 0 and 3, you're tracing the same value for the slope. So the y coordinate here over this graph is the slope above that x where you are calculating the derivative. Is that clear? Is that clear? Yes, should be very clear. Do you see why it's here, guys? So if I calculate at this point x, what's the slope? The slope is 1. If I calculate at this x, the slope is 1. What am I graphing as y? I'm graphing the slope against the x at which I calculated the slope. That's how I generate the graph of the derivative. Yes? Now, the graph I presented you, it was very trivial to calculate the derivative because it's made of line segments. Am I right? It was very easy to calculate the derivative as it was made of line segments. because all you have to do is note the slope of that particular line segment. You don't have to bother to look on points between the edges of the line segment. Am I right? Now, if I have a more complicated curve, I kind of drew the derivative as this green curve. Do you understand how I obtained that sketch? It's not a precise sketch because I haven't measured slopes precisely. But if I bothered to measure the slopes precisely, I could generate a pretty good approximation. Yes? What did I do, guys? I mean, that's what I'm trying to get. What point am I trying to get across, guys? Why do we study derivatives geometrically? Because if we are not dealing with a straight line, we can imagine that another curve is a chain of straight lines, a long chain of very short straight lines. Do you agree? So here I kind of try to illustrate it. Here is the actual curve, and I approximate it with several segments of straight lines. Do you agree? Look at it. Those are several segments of straight lines. And then for those straight lines, I mean, what is this point? This point is the approximation of that slope. Now I drew a continuous curve. I would say that if this were my approximation, look at it. If this were my approximation, what would I see over here, guys? Look at it. Over here, the slope is negative, right? So over here, over this point, I should see something like this, a straight line like this. Because everywhere here, if this is one straight line, everywhere here you have the same slope. Over here, I will now between this and that point, I will see a slope that's more negative. So I will see a straight line like this. Right? Over here, the slope is slightly more positive. So over here, I will see a straight line like this. So if you make those line segments, so basically no matter how many line segments you make, the actual curve that you would have been drawing if you just use that approximation will consist of many very short horizontal lines. But as you select more and more line segments to line along the curve, the length of those horizontal line segments will dwindle. They will be more and more like points. Do you follow what I'm saying now? You following what I'm saying, guys? So if you were to do that approximation by a computer and you would say, just build line segments along the curve, right? Then you would have just finitely many measurements of slope, and you would have the thickness, basically the width of the straight lines that you will see will correspond to the distance on the x-axis between over which you take different points, right? So you take one point and you take another point and you take another point. How do you create the straight lines? You partition the x-axis into many short line segments, and you calculate the vertical points at those edges. I hope you understand what I mean. I have a feeling you do not somehow. It's very simple. How would I do that process? I will just divide it into many line segments. Look at it. Over this line segment, hope, here is one point. Hope, here is another point. Here is my line segment. So the horizontal line would be of this width. Yes? You understand what I'm saying, guys? So that green curve, I can imagine getting the approximation for it by selecting ever narrower, mesh over the x-axis. I kind of slice the x-axis into very small segments, and I calculate the slopes over those small segments, and then I have horizontal lines that will look more and more like actual points. Do you see that? Well, I mean, up to you. What you see or what you don't. Yes, the derivative becomes the y for that graph. Exactly, the derivative becomes graph. What I'm saying, guys, is extremely trivial. Extremely trivial. A curve is built of line segments, the chain of line segments. And therefore, the graph of the derivative is the plot of slopes over those line segments. Yes? Now, it's a limiting process. It's not true that that those line segments that I drew built up that black curve. It's not true. It's only an approximation, right? Because it's not a full straight line over that region. All right. I posted also a book on my website. I think I mentioned it in the email. I hope you saw it or will see it soon. Good. You should not sit, guys, and wait for this to be explained with mouths open. And especially if you don't stay in office hours, it's not going to go like this. When I studied calculus, I studied 4 hours a day. I told it to myself, it was 4 hours every day. I mean, if you're not doing, and I was good at it. So if you're not doing it, then it's much more difficult, right? And you have some holes in your background. So you are supposed to try to plug those holes as fast as possible, guys. It's very difficult to get ready in this amount of time. All right, where are we now? The derivatives of polynomials. Notice we're approaching the end of this chapter. Well, after trigonometry is when I will announce your exam. Okay, guys. Remember what are polynomials? So a polynomial, would anybody tell me what it is before I mention it? Remind me what it is. This is chapter 2, it's in my notes, Francis. Remind me, please, before I open that lecture, what is a polynomial? That's beautiful, Christian, right? So sum and multiplication, all very, very good. Guys, always remember the gist of something and not the form, right? Now, do you remember why we write polynomials as we do? That's very simple, right? So what I try to say is, already beforehand, is look at it. You see this function uses x in several times, right? So if I regroup it, look at it. If I group the operations, I can see operations where no x was required, operations where 1x was required, operations where multiplication by x twice was required, and so on. I can it's a sort of seder or a cleaning of your household, right? You understand what I mean? So you want everything to be properly placed. And so what is my function? It's this. Look at it. I wrote it this way, but I can, of course, this all only uses addition and multiplication, and I can group it by the number of times I had to multiply by the variable x. No times, 1 time, 2 times, 3 times. That's why I prefer to also write it in this way, not starting with cube, but starting with smaller powers, okay? So you can see that's why polynomial can be defined to be this formula. It's really because addition and multiplication corresponds to that bookkeeping, to that organization easily. And that organization means you only used addition and multiplication. Clear? Wonderful. So in general, guys, this is the structure of a polynomial. That's the definition that you're given in school, but very often not motivated definition. Good? So tell me, please, let's begin trying to understand the derivatives of polynomials. What's the derivative of f of x equal to c without doing any calculations? 0. Why is it 0? Because f of x equal to c is a horizontal line and its slope is 0. Correct? It's derivative of that easy polynomial. That's trivial. That's 0. We can write it as d dx of c equal to c if we don't want to give it a name. How do I know f of x equal to c is horizontal? Think about it, Francis, right? So here is the x-axis. What happens if I plug the value 1? If I plug the value 1, what I'm going to get? I'm going to get c, right? If I plug the value 2, I'm also going to get c. If I plug any value in between, I get c. Any value here, I get c. Any value here, I get c. Do you see what I'm tracing? I'm tracing a horizontal line. Yes? Okay, great. So the derivative of c is 0. I'm just saying, okay, what's the slope if I look at any point x? I can write the derivative of a constant is 0. Now, please help me also without much calculation. What's the derivative of f of x equal to x? Beautiful. F of x equal to x is 1. By the way, if I said derivative of f of x equal to x plus 7, the derivative would be what? Also 1, right? Because it doesn't matter. All we care about is the slope when we take the derivative. Good? Oh well, right? The derivative of f of x equal to x is 1. Here, I actually bothered to calculate it just to remind you that you want to use formalisms. Good? We didn't do anything. Now it becomes a bit more difficult to tell. What's the derivative of f of x equal to x squared? Please tell me and calculate it. 2x. We already did it several times. This I cannot see, at least without doing the calculation. Right? It's not obvious by looking at the graph to me. Clear? The derivative is, here is how I do it. I just take the limit. In other words, what I'm saying, I'm just asking the mathematics to tell me what happens if I zoom on the graph. So I take limit as z goes to x. The reason I say z is just I want x to be that fixed point. I don't want to switch to a different letter. And I'm just saying, let me zoom in at the point x squared. So when I zoom in at that point, all other points I designate by z. Z becomes very, very close to that x. So I say limit as z goes to x of z squared minus x squared over z minus x. I factor it out, I see 2x. But we are going to try to notice a pattern. You understand, guys? We are now searching for shortcuts, which if you took calculus before, you might know the shortcuts. Good? But we are now going to derive those shortcuts. Next question, guys. Can you figure out what will happen if I want to take the derivative of x cubed? You see, I'm trying to find formulas for those things. Okay, that's an interesting guess, guys. 3x squared. Right? It seems that we dropped the number 3. Can you explain why? So calculate the derivative if you can by definition. Can you do that? We have kind of very little time. We might not have time. Can you calculate by definition? Yeah, long division. Right? If you do not know how to do that, you do long division. That's very good. You see, here is the long division, guys. If you don't remember, you always want to have some sort of tool. Do you remember long division? That's a good time to review long division. Good for your algebra, good for your overall mathematical well-being. All right, guys. I think we are going to pause since you're not going to finish it in 1 minute, and I'm not going to explain it fast enough in 1 minute. What we do now is 1 or 2 rounds of what, when, where. Definitely 1 round. And afterwards, office hours, of course.